Okay, this is the second video for section 4.7 looking at maximum and minimum problems. So we had looked at the extreme value theorem for calculus 1 and talked a little bit about extreme value theorem in the last video for 3D. So continuous, the extreme value theorem for functions of two variables, a continuous function f of x, y on a closed and bounded set D in the plane attains an absolute maximum value at some point of D and an absolute minimum value at some point of D. Finding the extreme values of a function of two variables. So this would be kind of our procedure. Suppose z equals f of x, y is differentiable, is a differentiable function of two variables defined on a closed bounded set D compact. Then f will attain an absolute maximum and minimum value on D. And these will occur at a point a comma b, where a comma b is a critical number of f in D, or a comma b is on the boundary of D. So what we looked at in the previous video is we looked at problems where we didn't have a boundary, so we just found the critical numbers and then we determined whether they were maximum, minimum, or possibly saddle points. Okay, so let's go ahead and we're just going to work on one example here, and it'll be plenty. So we're going to find the absolute extrema of the function f of x, y equals x squared plus xy on the region R, which is going to be the set of all x, y, such that the absolute value of x is less than or equal to 2, and the absolute value of y is less than or equal to 1. So we could translate this as the set of all x comma y, such that negative 2 is less than or equal to x, which is less than or equal to 2, and negative 1 is less than or equal to y, which is less than or equal to 1. So if we draw that region, we're just looking at a rectangular region. So what we want to do is we want to find all critical numbers, and then any critical number that's actually in this region R we'll consider. If it's not in this region R, let's say we got a critical number of 3, 5. Well, 3, 5 is not in this, so we wouldn't worry about it. We're only restricting, or we're only looking at the region R. Okay. So first we'll look at first partial with respect to x, which is 2x plus 1. 2x plus y. That's going to be equal to 0 when y is equal to negative 2x. And the first partial with respect to y is going to be just x. That's going to be equal to 0 when x is equal to 0. So then that implies that y has to be equal to 0. So that 0, 0 is certainly in our region, so we will consider it. So this is going to be the previous method where you just look at, okay, the second partial with respect to x, which is going to be 2, the second partial with respect to y, which is going to be 0, and the mixed partial, which is going to be 1. Okay, so we look at 0, 0, evaluated at the second partial with respect to x is 2, evaluate that at the second partial with respect to y, that's 0, and evaluated at the mixed partial at 0, 0, and that's going to be 1. D is equal to the second partial with respect to x times the second partial with respect to y minus the square of the mixed partial. Okay, so it's going to be 2 times 0 minus 1 squared, which is equal to negative 1. So if the D is negative, that tells us that we have a saddle point. So it's not really an extrema, but we'll go ahead and say we have a saddle point here. Okay. And if we evaluate the function at 0, 0, we're going to get 0, so we got a saddle point at the origin. Okay. So now what we need to do is we need to check the boundaries. So we're going to check along each one of the boundaries. We'll go ahead and check along the boundary x is equal to 2. So if x is equal to 2, we'll have f of 2 comma y, which is going to be 4 plus 2y. And that's just a line. And the y is going to be between negative 1 and 1. So we're going to graph on the yz plane. So y goes from negative 1 to 1. And it's just linear. Okay. So evaluate at -1 for the y, and we get 2. Evaluate at 1, and we get 6. We have a line there. And so for the lines, the extreme are going to happen at the endpoints. So f of 2 comma -1 is going to be 2. And then f of 2 comma 1 is going to be 6. Okay? So you have a minimum at -1 and 2. That's -1 for the y and 2 for the z. And then we have a max at 1 for the y and 6 for the z. Okay, and then we'll have to compare this with everything else that we get off the boundaries. Alright, next boundary we'll look at is x is equal to -2. So f of -2 comma y is going to be 4 minus 2y. So again, we'll go ahead and graph that. Okay, so I don't know if I label it later, but this is going to be y and z. Okay. And we put 6 on, so we evaluate this at -1. So we're going to get 6, and evaluate at 1, and we're going to get 2. And so we got another line, so the maximum is going to happen at one of the endpoints. Likewise, the minimum will happen at one of the endpoints. So we got our max and our min. So f of -2, -1 is equal to 6. And f of -2, 1 is equal to 2. Okay? So we've looked at two of the boundaries. X is equal to 2, x is equal to -2. Now we're going to look at the boundaries. Y is equal to 1 and y is equal to -1. Okay, so we'll draw our region again. Okay. Write down our function, f of xy is equal to x squared plus xy. So now we're going to look at the boundary, y is equal to 1. So f of x comma 1 is going to be x squared plus x. Now this is a quadratic, so the quadratic is going to be a little bit different than the line. So the quadratic, we're going to go ahead and look at the critical numbers of the quadratic. And we would have looked at this exact same function in the first video, so it has a critical value at -1/2, and so then we're going to evaluate x squared plus x on the xz plane, and the x is going to go from -2 to 2. Okay, so f of -2, 1 is going to be 2. And then we got to evaluate at the critical number, which is -1/2. So f of -1/2, 1 is going to be -1/4. And f of 2, 1 is going to be 6. Okay, so we have, that is not our min. Just kidding. This is our min down here. And then this would be, over here would be a local max. And then we got our max up there. Okay, now let's look at the next boundary. Y is equal to -1. So f of x comma -1 is going to be x squared minus x. We'll go ahead and find the critical number of this because it's a quadratic. It's going to be 2x minus 1, and that's going to be equal to 0. So that tells us our critical number is going to be x is equal to 1/2. Okay, so again, we're going to be on the xz plane. X is between -2 and 2, so we're going to check the endpoints and also the critical number. So f of -2 comma -1 is going to be 6. F of 1/2 comma -1 is going to be -1/4. And f of 2 comma -1 is going to be 2. Okay. Oh, I did it again here. At least I'm consistent. Oops, go back. That's not the min. The min's down here. Okay. So we got a bunch of information on 2 slides. Let's go ahead and put it all on 1 slide here. Okay. All right, so we're just going to write all that information down, okay? So that's everything we got from the past 2 slides. We got our saddle. And then we're going to be looking at all the boundaries. So we got the boundaries in red, green, orange, and blue. Okay, and so we're just going to go through and we're going to determine what's the largest, what appears to be 6. Okay, so we'll go ahead and put max next to those. Okay, and notice that in both we got the same point 2, 1. So 2, 1, and 6 is a max. -2, -1, and 6 is a max, and that's we got it again. You looking at a different boundary. Okay. All right. So our maximum points are going to be 2, 1, and 6, comma -2, -1, and 6. Okay, now the smallest value it looks like we got was -1/4, so we do have 2 minimums. So we have minimum points at -1/2, 1, and -1/4, and 1/2, -1, and -1/4. Okay, and then we'll also put our saddle point on there. Okay. And we'll write down our function. F of xy is equal to x squared plus xy. Alrighty, well that concludes this video. So 2 videos for section 4.7. I think 4.8, which is going to be the Lagrange multipliers. I think we're going to have 3 videos for that. So we'll see you next time.